Hi everyone, and welcome to Calculus Lesson 5-4. We're talking about work today. Now, I know you think that schoolwork is work and all other types of work are work, but we're looking at the physics definition. So in physics, work equals force over a distance. So it's force times distance. But let's take a closer look at what we mean by force. Technically, force is a push or pull on an object. Now, when we talk about force, it also depends on what units we're working in. If we're working in what we used to call English units, okay, or if we're working in CI units or metric. Okay, because if we're working in English units, we're going to be working in feet for our distance and pounds. Okay, and pounds is a weight, which means that if they give you pounds, it's also considered a force on an object. If we're working in metric units, though, we're going to be working in meters for our distance. And we're going to be working in kilograms for our weight measurement. Now, because that's technically not a force, when we're given kilograms, we always have to multiply by the gravity constant to turn this into a force. Okay, so you have to be very careful about the units because depending upon which units you're given, your calculations will change. If we're working in English units with feet and pounds, we can just take the distance in feet and multiply by the number of pounds. If we're working in metric units, you can take the distance in meters, multiply by the kilograms, but then you also have to multiply by the gravity constant. And in the case of Earth, the gravity constant is 9.8 meters per second squared. Okay, usually they give that to you in the question, but sometimes they might not. So let's take a look at a basic example of this. Okay, example 1 said, how much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? So the first thing I'm going to do is look at this and try and decide if they're working in metric or English. And I notice that we have kilograms here and we have meters here. So that means we're working in metric. So now I need force times distance. So my distance is 0.7 meters. That's my distance. But for my force, I have to do 1.2 times the 9.8 meters per second squared of gravity. If I multiply all of this together, I will get the work done, which is 8.2. And this will be measured in joules, also known as Newton meters. Okay, let's look at another example. Part B says, how much work is done in lifting a 20-pound weight 6 feet off the ground? Now notice I have pounds and feet. So I'm working in English units. Okay. So this is my distance, 6, and my force is 20 pounds. So force times distance gets me 120 foot-pounds. Okay, and there's no special unit for this. We just multiplied feet times pounds, so we call it foot-pounds. Up here, we multiplied newtons times meters to get Newton meters, but they do have a special name for that. It's joules. Now notice, these are all constant forces. We have a constant force of 20 pounds. We have a constant force of these two things multiplied together. But what if the force is not constant? And that's where we come to calculus. Okay, what we do is instead of using work equals force times distance, what we're going to do is set up an integral. So if the force is not constant, then work is the integral from A to B of our force function dx. Okay, now A to B are going to be defined generally by the distance that the object is moving. Okay, this is the starting point. And this is going to be the ending point of its move. Okay, the f of x, as I said earlier, is the force function. This describes the force. Okay, and dx, of course, is the notation to say we're taking it a little bit at a time, infinitely small. So let's take a look at an example of this. Example 2 says, when a particle is located a distance of x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? So looking at that work formula I had earlier, my calculus one, notice that this x equals 1 and x equals 3 at the bottom here would be my starting point and my ending point. So I'm going to do the integral from 1 to 3. Now this is my force function, x squared plus 2x. So I'm going to put that here, x squared plus 2x. Oops, that's an x. And it's dx. So now all I need to do is do my antiderivative and evaluate it from 1 to 3. So this becomes 1/3 x cubed plus x squared, evaluated from 1 to 3. 3 to the third is 27, divided by 3 is 9, plus 3 squared, which is 9, and then minus 1/3 plus 1. Okay, so this is 18 minus 1 and 1/3, which is 16 and 2/3. Okay, now we're working in feet, so this has to be in foot-pounds. Okay, so that's it for that example. Come back for some more examples. We're going to be talking about Hooke's law with springs. And we're going to be talking about working with cables suspended from a building and volume.